Good morning, all. Welcome back to our official YouTube channel of SRN BGNR Government Degree College, myself, Dr. B. Satish Kumar, Assistant Professor in Biochemistry. In last few classes, we have been discussing about the introduction to enzymes. We have enzymology syllabus, 2 units of enzymology syllabus for second year students in third semester. So far, we have discussed about the third unit, um, where we have learned about the fundamentals of enzymes, and now the fourth unit of this paper, where we are going to study enzyme kinetics and as well as inhibition of enzymes. First of all, we start with the first subtopic in this fourth unit is the factors which are affecting the catalytic effect of the enzyme. So that is the factors affecting the enzyme catalysis. There are several different factors which affect the enzyme activity, and important factors are mainly four. We have substrate concentration, enzyme concentration, and effect of temperature and effect of pH. In this video, we will be discussing about these four factors, how they will affect the enzyme activity. If we increase one of these factors, what happens to the enzyme activity, whether it is increases or decreases, or whatever it happens, we are going to discuss in this video lesson. The first one is effect of substrate concentration on the enzyme activity. Here, the substrate concentration means, suppose we have some amount of enzyme, a fixed amount of enzyme is there. Say for example 10 units of enzyme, that means 10 molecules of enzyme is there. What happens if we add some amount of substrate to the enzyme? The enzyme will first bind the substrate and convert it into product within a time span, say for example in 1 second. So what happens in 1 second? One enzyme molecule converts one substrate molecule to product. So that is the rate of the enzymatic reaction. One subunit, one substrate per 1 second. Like earlier, we have discussed about the units of enzymes, enzyme activities. That is catal. Catal is moles per second. So if we take that same enzyme units here, how many moles of enzymes, how many moles of substrate is being converted to product in a second by the enzymes? Suppose if we take lesser amount of substrate when we compare to the concentration of the enzyme, what happens? The enzyme will convert and total amount of substrate molecules to product in 1 second. Suppose 10 enzymes are there. If we use only 5, suppose we have 10 enzymes and we are using only 5 substrate molecules, within 1 second, these 10 enzymes will convert these 5 substrate to 5 products only. Okay, so that means we have excess enzyme is there and less substrate is there. So the enzyme is not completely saturated by the substrate. Half of the enzyme, that means 5 enzyme molecules, are still free to do the reaction. Only 5 are engaged in the enzymatic reaction. So in this case, if we use less amount of substrate, that is below the saturation level, what happens? The enzyme activity will be less, 5 moles per second. If you use 6 moles, what happens? In the same time, 6 moles of enzyme product will be converted. If you use 7 moles, this will be 7. So gradually, if we increase the substrate concentration up to the saturation level, the enzymatic activity also increases. Okay, up to 10 molecules. So if we use 10 molecules of substrate, so then what happens? It will be 10 molecules of products per second. If we use 11 molecules of substrate, then still it will be 10 only. Okay, so that means it reached a maximum. If we use 1000 molecules of substrate, then still it will be 10 molecules per second only, because we have only 10 substrate, enzyme molecules. So this way, below the saturation level, we have the enzyme activity increases, and then above the saturation level, the enzyme activity will be stable. So that is the effect of substrate on the activity of the enzyme. So therefore we will get a rectangular hyperbola graph. In this graph, in this curve, we will see three different regions. First one is linear stage, that is A. First one is the linear stage, so that is this region. What happens in this region? If we increase the substrate concentration, the product concentration also increases, so that the enzyme activity also being increased, because this is below the saturation level. And at the second stage, this is curve stage, so little bit bend, it is bend little bit, it is not straight like this, it is bend a little bit, because it is reaching the saturation level. So that means the amount of substrate is reaching is saturation level towards the enzyme. So the amount of enzyme is almost satisfying all the enzyme molecules. So most of the substrate molecules are binding to all the enzyme binding sites, that is active sites. So at the saturation level, what happens? uh, mm, as it approaches to the saturation levels, the activity slowly increases, but not proportionately. When and the third one is unchanged stage. So this is beyond the saturation. Beyond the saturation, if we add further amount of substrate, it will not change the amount of product that is formed in a second. So that means over the time, at excess substrate concentration, the enzyme activity will be maximum. Further increase in the substrate concentration may not change the enzyme activity. So therefore, we will get the C, where it is stationary, unchanged. So overall, as we gradually increase the substrate concentration, and keeping the enzyme concentration at a constant. So enzyme concentration is constant, but the substrate concentration is gradually increasing. So finally we will get a hyperbola like graph. So this is the activity of enzyme which is affected by substrate concentration. So if we want to know the maximum velocity of the enzyme, we have to use excess amount of substrate. And the second factor affecting the enzyme activity is the enzyme concentration itself. So in the previous one, we we have seen about the effect of substrate on the enzyme activity. In that case, the enzyme concentration is unchanged. Okay, the enzyme concentration is constant, but we are changing the substrate concentration. But in this case, in this second case, the substrate is not at all limiting. So that means we are using excessive amount of substrate. The substrate uh, supply is almost several fold excess than the required levels. So that means we have excess substrate concentration, and we gradually increasing the concentration of the enzyme, and seeing whether how much seeing how much enzyme activity is increased or decreased. So this is very easy to explain. We will get a linear straight line curve in this case, because suppose we use suppose we use 10 enzyme molecules and 1000 substrates, what we will get? 10 molecules per second product. Okay, and in the second case the 1000 is unchanged, and if we use 20 molecules, then we will get 20 molecules of product per second. So this way, if we increase the concentration of the enzyme and keeping the concentration of substrate at very excessive state, what happens? The product formation will also be more, that increases proportionately. So that is why it increases in a linear straight line straight line. Okay, it gives a linear straight line. So in this straight line we can easily see on the x-axis we have E, concentration of the enzyme, this is gradually increasing, and on the y-axis we have velocity of the enzyme. So that means the rate of the reaction, the velocity of the product, how much product is formed per second. Okay, so as the enzyme concentration increase, the velocity also increases. So that is why we are getting a straight line. Okay, completely proportional. The the enzyme activity is completely proportional to the concentration of the enzyme at excessive substrate concentration level. So that is why the enzyme concentration affects the activity of the enzyme. And the third one is temperature. This is one of the physical condition which is very important when we study the enzyme kinetics, because all the enzymes are proteins. They are made with amino acids, and amino acids uh, they will form chain like structures and finally form the protein structure. Protein is a three-dimensional folded structure of amino acid sequence. So if we change the temperature up to some extent, the activity of the enzyme increases, and beyond that one particular temperature, the protein gets denatured. At higher temperature, the what happens, the interaction between amino acids will be disrupted. So therefore the structural integrity will be lost at higher temperature. So at higher temperature the enzyme activity will be less. At lower temperature also the enzyme activity is less. But at one particular point where we call it as optimum temperature, at the optimum temperature any particular enzyme will be at maximum velocity. Okay, so in so every each and every enzyme will have one optimum temperature. In that temperature range only the enzyme will be more active. So beyond that or below that the enzyme activity is less. So therefore what happens, the curve will be in bell shape. A bell shape curve will be obtained. Okay, uh, when we study the effect of temperature on enzyme activity, we will have this bell shaped curve. So on x-axis we are using temperature in degree centigrade. So that means uh, we have enzyme plus substrate. We have fixed amount of enzyme and excess amount of substrate. It will proceed the normal reaction, but the same reaction is being conducted at a different temperature. So this is, suppose for example this is 0 degree centigrade, and we are gradually increasing the temperature and monitoring how much product is being formed. Okay, so in this way what happens, at initial stage the enzyme activity is less, and as we increase the temperature, the enzymatic activity will also be increased up to some extent. Once the enzyme reaches the optimum temperature, suppose this is the optimum temperature around 37 degree centigrade. Suppose at 37 degree centigrade the enzyme reached its optimum temperature, so it is having maximum velocity. Once again, if we increase the temperature beyond the optimum temperature, the enzyme activity gradually declines because the structural integrity of the enzyme will be lost. The interaction between the amino acids in the protein structure, that enzyme structure, will be disrupted. So enzymes will be no more functional. As the temperature increases, the enzyme denatures. Due to the denaturing nature, the enzymes will be non-functional and the product formation will be very less. So if we further increase the temperature beyond the optimum temperature, that will decrease the activity of the enzyme. So therefore we are having a bell-shaped structure. So in when we talk about the effect of temperature on enzyme activity, we have to know one important term, that is temperature coefficient. It is also known as Q10. Q10, why we are calling 10? 10 means 10 degrees centigrade. Okay. Suppose if we increase the temperature of any particular enzyme by 10 degrees centigrade, the activity will be doubled. So that means we have one enzyme uh, that is the velocity of the enzyme, the rate of the reaction, the activity of the enzyme is measured at 20 degrees centigrade. Suppose this gives 10 units of activity. At 30 degrees centigrade, what happens? The difference is 10 degrees centigrade. At 30 degrees centigrade, it will double. So that means it will give 20 molecules per second. Okay, this is called temperature coefficient, or Q10. So Q10 explains that almost all enzymes will follow this uh, kind this situation, where increase in temperature, if we increase the temperature of enzymatic reaction by 10 degrees centigrade, the enzyme activity will be doubled. This only true within a range, temperature range, that is 10 degree to 40 degree centigrade. So in this range only the temperature coefficient Q10 definition works well. Beyond the 40 degree centigrade, it may not work because the denaturation of the protein. So the Q10 is always 2 for almost all kinds of enzymes. And next thing is factor is pH. The pH is also very important factor to consider when we are studying the activity of the enzyme, because the enzyme is made up of with amino acids. All amino acids will have different net charges at different pHs. We already know about the zwitterions and isoelectric point. We have seen all these things in the first year itself. So for any amino acid, the pH, based on the pH, the charge of the amino acid will be changed. At isoelectric point, the net charge will be 0. Below the isoelectric point, the amino acid gets positive charge. Above the isoelectric point, the amino acid will get negative charge. So there is no fixed charge for any amino acid. It depends on the pH of the medium in which the amino acid is present. In the same way, all the proteins or enzymes are made with amino acids. So therefore, based on the amino acid composition, there will be a specific pH at which the enzyme activity will be more. Beyond that pH or below that pH, the activity also decreases. Like earlier we have discussed about the effect of temperature. So same thing applies here. There will be one optimum pH. So optimum pH is the pH where the velocity or the activity of the enzyme will be maximum. Below the pH or above the pH will going to affect the activity of the enzyme. So therefore we will get a bell-shaped curve when we measuring the activity of the enzyme while changing the pH. So on the x-axis we have pH, gradually increasing the pH from 0 to 14, and on the y-axis we have the enzyme activity. Okay, so in this case, suppose the optimum pH for some x enzyme is around 7.2. So that means from 0 to 7.2 the enzyme activity gradually increases. At 7.2 the enzyme activity will be at maximum. Beyond the 7.2 it gradually declines once again and comes to almost 0 level. So here this 7.2 is called the optimum pH of enzyme. So each and every enzyme will have optimum temperature, their own optimum temperature and their own optimum pH. So suppose for example, if we take pepsin, a digestive enzyme which is present in the stomach, okay, it is present in the acidic environment, HCl. So therefore it will be active in the acidic environment, that is pH 1 to 2. In pH 1, in the range of pH 1 to 2 will be more active, the pepsin enzyme will be more active. If you increase the pH of the stomach beyond 2, the pepsin won't work. In the same way we have acid phosphatase enzyme. So in the name itself we have acid, so that means it works at the acidic pH. So that is around 4 to 5. 4 to 5 range is the optimum pH for the acid phosphatase. And alkaline phosphatase, last one is alkaline phosphatase, means it is also a phosphatase enzyme, but it works well in the alkaline condition. Both are same enzymes, same substrate, same products, but both will perform their function at different pH ranges. Acid phosphatase performs its function uh, at 4 to 5 pH range, and alkaline phosphate will be more active at the pH range 10 to 11. So this way these four different factors, those are substrate concentration, enzyme concentration, temperature and pH. These four are very important factors that affect the activity of the enzymes. So with this we have finished the third unit, and we will move forward into fourth unit, where we will study enzyme kinetics and as well as the inhibition of enzymes. Like chemical kinetics, we have enzyme kinetics also. The study of enzyme kinetics is very important in research and medical field also. We have one particular equation derived by Michaelis-Menten, known as Michaelis-Menten equation, that will give an idea about the velocity of the enzyme. Suppose if you want to know the velocity of the enzyme, we have to know some variables according to the Michaelis-Menten equation. So Michaelis-Menten equation is V equal to V max into S by Km plus S. So V is velocity of the reaction, velocity of the enzymatic reaction. So how much substrate is converted to product per unit time, and S is nothing but the concentration of the substrate that is we are using, and the Km is Michaelis-Menten constant. This is a constant for all enzymes. This is not specific for any specific enzymes. It is not changed at all. Sorry. This for specific enzymes it will be uh, stand constant. It will not change with the changing conditions. And so the Vmax is the maximum velocity. So at maximum concentration or excess substrate concentration levels, the enzyme will have maximum velocity, that is called Vmax. Let's have a look at the derivation part of the Michaelis-Menten equation. There are some important things to discuss to derive the Michaelis-Menten equation. The first one is the enzymatic reaction equation proposed by Brown in 1902. He proposed that at much higher concentration of substrate, that means excess amount of substrate concentration, two elementary reaction takes place. First part is E plus S gives rise to ES. This is one reaction, and then ES is converted to product and enzyme. That is another stage of the reaction. So first the enzyme binds substrate, enzyme binds substrate, and it forms enzyme substrate complex. This is stage 1, and in the stage 2, this enzyme substrate becomes product and enzyme. So that substrate becomes a product and the product released from the enzyme. These two stages are there in any enzymatic reaction. First one is enzyme substrate complex formation, then the product formation, these two. Okay, so when we consider these two stages, elementary reactions in the enzymatic reaction, the second step, that is the formation of product from enzyme substrate complex, is the rate limiting step. Okay. Next important point to consider is law of mass action. Like in chemical kinetics, that the rate of the chemical reaction is directly proportional to the product of concentration of the reactants. Carefully observe that the rate of the reaction is proportional to the product of concentration of the reactants. So this is the reactant. In earlier enzymatic reaction, what happened? The second stage is ES gives rise to E plus P. Okay, product and enzyme. So ES is the reactant and P is the product. So the velocity of this reaction is K2. Okay, this the constant is K2 and the velocity V equal to, so this is proportional to the concentration of the ES, not the concentration of E, not the concentration of P. So it always depends on the concentration of the reactants, not the product. So therefore V equal to K2 ES. K2 is the constant for that reaction. So V is proportional to ES, and then V equal to K2 into ES. So this is we are going to solve. So we have to solve for V. But V is nothing but V is equal to K2 into ES. Okay, K2 is constant, but we don't know the concentration of the enzyme substrate concentration. So that is why we have to solve for ES first. Then we can easily find out what is V. So this is the equation 1. In the equation 1, we have to solve for ES concentration, enzyme substrate complex concentration. Okay, so and third point is the steady state assumption. According to the steady state assumption proposed by Briggs and Holden, the rate of the synthesis of enzyme substrate concentration, enzyme substrate complex is equal to its rate of consumption. So that means the enzyme substrate level will be constant during the and during most of the time of enzymatic reaction. So if we use excess amount of the substrate, then what happens? The number of enzyme substrate complex molecules will be same. If so, how the ES complex is formed? Here enzyme binds substrate and forms ES. How ES will be dissociated? Enzyme substrate is dissociated into product and enzyme, and at the same time in the backward reaction the enzyme substrate may not be converted into product and enzyme. Sometimes enzyme substrate uh, will dissociate to form enzyme plus substrate. Okay, so that is why the form here, according to this rule, steady state theory, that the concentration of the enzyme substrate complex will be at a steady state, so at equilibrium. If 10 molecules of ES is synthesized, then 10 molecules will get breakdown. Always it will be at a constant concentration. So that is what the steady state assumption. So that means the formation rate of formation of ES is equal to the rate of its consumption. Okay, so according to law of mass action, we will try to calculate, we try to get the equation for this steady state assumption. So first thing is rate of formation of ES. How the ES is formed? E plus S gives rise to S. Okay, so that is why V equal to K1, V equal to K1 E into S. These are reactants, so E into S. Okay, the velocity of the formation of ES depends on the concentration of reactants, that is E and S. So K1 E into S is equal to the rate of consumption, rate of ES consumption. So ES will be consumed by two reactions. Okay, the first reaction is, so it is coming back, so that is why K minus 1 into ES. ES is the reactant here. Products are substrate and enzyme plus, and this ES, what happens? Product will also be formed. So here is here also the ES is a reactant. For this we have K2 ES. So that is why this is according to steady state assumption, K1 E into S equal to K minus 1 ES plus K2 ES. Okay, so this is the equation 2. So in this equation, if we clearly observe, we have common, we have ES is common at this right hand side. So we can make it as a common, the next line. Okay, and one more thing here. Anyway, we will solve for ES, and we have to know E also. E means the free enzyme that is free to bind substrate. Okay, so that is why in this equation we can measure the ES but not E. Okay, ES and E are directly not measurable, but the total amount of enzyme, that is ET, can be measured. Here ET equal to free enzyme and bound enzyme. ET equal to total enzyme molecule. Out of total enzyme molecule, some enzymes molecules will be free and ready to bind substrate, and remaining enzymes will already be in bound state, ES state. So ET equal to E minus E plus E equal to E plus Et. So if you want to know the concentration of free enzyme, E equal to Et minus Es. So this is the third equation. Okay. So now in the last slide, in the steady state assumption, we came up to this equation. So now we can take the Es as common, E into S. Okay. So now here we have Es here, Es here. So now we are taking these two Es as common, Es into k minus 1 plus k2. Okay. So now if we put the equation 3, this one, in equation 2, this is the equation 2. If we put it in here, substitute here, we will get for E, V is Et minus Es. So we have K into Et minus Es and substrate concentration equal to K minus 1 plus K2 into Es. So now we are multiplying the S, taking the S into brackets. So we will get K1 ETS, K1 ETS and minus K1 ES S equal to this one. So now further solving, we will get, we will take in the next slide. So now what we will do, we will take in this slide, we take this K1 ESS to right hand side. Okay. So here we taken it to the right side. Okay. And the ES is also common in this word and this word also. So that is why we taken ES as common and we are getting K1 ETS equal to ES into K minus 1 plus K2 plus K1 into S. Okay. And finally, dividing both sides by K1, we will get this equation. Okay. So here all three constants are in this way, K minus 1 plus K2 by K1. Because these three are constants, we can use a single constant for these three. That constant is the Km here. Km means K minus 1 plus K2 by K1. Okay. So instead of writing these three, we are writing only Km. So Km is known as Michaelis-Menten constant. Okay. So now by solving for ES, ES, that is the important thing we have to solve for, because V equal to K2 into ES, that is the first equation. In that equation we have to solve for ES. So for solving for ES, we will get ETS by Km plus S. So then now we have to see the initial velocity of the reaction. Initial velocity of the reaction means when we start the reaction, that will have some velocity, that is initial velocity. Okay. At the beginning of the reaction, it will have the initial velocity. So initial velocity is given as V0 equal to K2 into ES. So this is the first equation, V equal to K2 ES, that is the first equation, V0 equal to K2 ES. And we already know that ES, already we have solved here ES, and we substitute this in the place of ES. So for that we will get this fourth equation. Okay, then what of the maximum velocity? Maximum velocity means if all the enzyme molecules are saturated with the substrate, so then the enzyme will have maximum velocity. So that means the E is equal to, sorry, the ES is equal to ET. All the enzyme molecules will be in bound state. So that is the at the Vmax. So Vmax equal to K2 into ET. Okay. So V0 equal to K2 into S. When we write V0 into Vmax, then ES is equal to ET. So Vmax equal to K2 into ET. So therefore, combining fourth reaction and fifth reaction, we will get the final equation like this. That is V0 equal to Vmax S by Km plus S. So this is called Michaelis-Menten equation. So in this video lesson, we have covered the factors affecting enzyme activity. First of all, we have discussed about the factors affecting enzyme activity. We have four different factors that affect the enzyme activity. That is, first one is substrate concentration, second one is enzyme concentration, third one is effect of temperature, and fourth one is the effect of pH. The substrate concentration, keeping the enzyme concentration at constant, and we gradually increase the substrate concentration, so then we will get hyperbola like curve where we will have three regions. First one is linear stage, second one is curve stage, and third one is unchanged stage. Okay. So up to some extent, that is below the saturation level, the enzyme activity proportionally increases with the substrate concentration. Above the saturation levels, once it reaches the saturation levels, it will be at a maximum, and further increase may not change the cannot it doesn't change with the increased substrate concentration. And enzyme concentration, if we keep the substrate concentration at excessive state and gradually increasing, the enzyme will proportionally increase the enzyme activity, so that we will get a straight line. And the temperature, for every enzyme there will be a optimum temperature where the enzyme activity will be more. Below or above this optimum temperature, the enzyme activity will be rapidly declined. And pH is also same, where each and every enzyme will have optimum pH below or above this optimum pH range. Each and every enzyme, the activity of the enzyme will rapidly decline. And the enzyme kinetics, the most important equation in enzyme kinetics is Michaelis-Menten equation, which is V equal to V max S by Km plus S. So we have solved the enzyme equation, kinetic equation, that is Michaelis-Menten equation, by using this assumption that enzyme reaction is having two elementary reaction. In the first reaction, the enzyme interacts with the substrate and forms the enzyme substrate complex, and in the second reaction, the enzyme substrate complex will form product, and the product will dissociate from the enzyme, and this is the rate limiting stage. And second one is law of mass action. It states that the velocity of the reaction is directly proportional to the concentration of the reactants, not the product. So therefore V equal to K2 into ES. From the ES only the product will be formed. So that is why V equal to K2 into ES. And the third one is steady state assumption. This is very important thing in solving the equation. That means the enzyme substrate concentration, enzyme substrate complex concentration will be at a steady state most of the time during the enzymatic reaction. Um, so that is why the formation of enzyme substrate complex and the dissociation of enzyme substrate complex is equal in most of the times. So keeping all these three things in mind, we can solve that uh, reaction, that's equation, where we will get the v max s by km plus s. So here v0 equal to v0 is the initial velocity of the enzyme, and vmax equal to the maximum velocity of the enzyme at excessive substrate concentration. S is substrate concentration, and Km is Michaelis-Menten constant, that is constant for particular enzyme. And next one is S, the substrate concentration. If we know the substrate concentration, Michaelis-Menten constant, and Vmax, then we can find out the initial velocity of the reaction. In the next video lesson, we will be discussing about the significance of Km and Vmax, and then we will move on to the inhibition of enzyme action.